we're about to finish up chapter 7. I'm kind of doing 7 in interesting order, not necessarily do section by section, because it's all kind of like wrapped up in the same ideas. What we've done so far, we've done a lot. We just got to remember what we've done. So how many trig functions do we know? 6. And can you rattle them all up for me if I ask you to? Sine, cosine, tangent. Yeah, cosecant and secant are the weird ones, right? We don't use them as much, but they're all weird at the moment to some of you guys if you've never seen them before. What are trig functions at the core? What are they? What do they represent? They take an angle and they tell you, I heard a word over there, the ratio of what? Sides, right? It's like sine. Okay, so let's do this kind of problem. Divide a triangle. Oh, that's really to scale, Jeff. There you go. So I got this triangle here. There's good old theta, right? Can you tell me what sine theta is? Yes, what is 5 over 13? Yes. Right, because what sine relate to? Which side of the triangle? If the angle's in the base, which side does sine talk about? The y side. Sure, you can say opposite. Right? If you know SOHCAHTOA, great. I don't know if you're going to trust me or not. Some of you guys are like, I love SOHCAHTOA. Shut up, you're crazy. I know a lot of math. I know it's going to help you later. Right? If you remember, sine is the y side, cosine is the x side. So much more makes so much more sense. So the y side's 5, hypotenuse is 13. Can somebody tell me right now, let me see. This is a little bit weird of a question. What's the biggest sine output can be? It's always how big this side is to how big this side is, right? Can it be bigger than 1? No. What's always going to be the biggest side in a right triangle? The hypotenuse, right? And isn't sine taking one piece of it divided by the hypotenuse? Can it ever be bigger than 1? In order for it to be bigger than 1, this side would have to be bigger than this side. Does that make sense? So the biggest it could be is 1. Can't be bigger than 1. How can it be 1? Well, that gets a little weird. Can you imagine me smushing this, just pushing it down, smushing it. Are you guys with me? Smoosh it, and I smoosh it all the way. So like here it is, it's a little sliver of a thing. I've smooshed it. Poor little dude. This is theta. And I just keep smooshing until it's just a flat line. That's when sine would be 1. Or in this case, I'm sorry, sine is 0. I'm going the wrong way. Sine is 0 is 0. How much of a y piece is 0 if I smoosh it all the way down? How big is the y piece? There is no y piece. If I smoosh it all the way, didn't the y piece get really tiny when I smooshed it? Okay, maybe. Okay. What's cosine of this angle in this triangle here? 12 over 13. I like it. I like it. Now, if I smoosh this, I don't know if you guys are with me on the whole smoosh thing, but if I just crush this, so if I make it rotate a bit, what happens to this side? If I push it down a little bit, what happens to that side? Okay, this is a little much. Okay, I'm with you. We'll come back to that. Okay, we'll come back to that. We'll take this smush stuff away. And then what's tangent? Yeah, it's going to be the y side over the x side. And then why are these kind of nice? What goes here? Oh, I already gave it away. The way I remember this is S goes to C, C goes to S. So the reciprocal of sine is cosecant, S goes to C. So cosecant theta is just the reciprocal of this. What's the reciprocal of cosine? secant. So reciprocal of this. And then what's the reciprocal of tangent? That one's a nice one. Cotangent. If you do take calculus, you will eventually understand why secant and why we call that cosecant sine and why we call that cosine. Right now, it doesn't seem to make sense. It seems like that should be cosine, but there is a specific reason, and you won't know until you do some calculus. So if you never do calculus, you'll never know. Okay. Maybe. So is that kind of problem? Okay. What if I gave you a problem and I didn't tell you what this was? If I know what that is, it's that simple, yes? If I give you a full triangle, making these ratios easy. Do you guys agree with me? Okay. So if I don't give you this side, what would you do? If I don't give you any of the, if I give you only two of the sides, how would you figure out the last side? Say again? I think you said it. Pythagorean theorem, 11. Yeah, okay. So for example, if I gave you this triangle here, let's call this A, and let's say this is 7 and this is 11. And I want to know all the 6 trig values of the angle A. All right, so for example, if I said sine, you could tell me, couldn't you? What's sine of A? 7 over 11, right? Is that cool? The y piece over the hypotenuse. But what's cosine? Why can't I do cosine of A? Because I don't know freaking x, right? Cosine wants the x side. So how do I figure out the x side? You said it earlier, right? So what would I set up to figure out the x side? So I don't know what this is. So what would I set up? Say, I'm sorry. X squared plus 7 squared 11 squared. Good old Pythagorean theorem, right? What's the most important side in a sense? What's got to be off by itself always? Hypotenuse, 11. So if we really care, it's not 11 squared plus 7 squared. No, x is not the biggest side. Okay, I like it. So then this will be x squared equals, what's 11 squared? 121. What's 7 squared? I'm going to subtract 49. Is that cool? And then what's 121 minus 49? 72. I like it. And then I take the square root. I don't put plus or minus because this is a side length. All right, we're going to talk about some negative stuff today, and I'll try to make it make complete sense. Can you simplify the square root of 72? Isn't there a nice square that you can break 72 up into, a square and something else? 72 is twice what? 72 is twice 36. So can't you make this square root of 36 times the square root of 2? And what's the square root of 36? 6. All right, this is the kind of stuff you need to be able to do quick, right? It's just Pythagorean theorem. Who cares? When you get a square root, you simplify it. We've done that before. Some of them won't be simplifiable. Great, don't. Only do it if you can. So now can you tell me what cosine is? Let me put this here, 6 rad 2 over, let's just subtract 2. So cosine would be 6 rad 2 over 11. Sweet. If I just put that, how can I tell very quickly I made a mistake? What's the biggest cosine can be? 1. So why is that obviously a mistake? It's way bigger than 1. Right? So if I just put that, I forgot to put it over 11. Okay, I like it. What's the tangent? What's wrong with this? It's not wrong. It's the right answer, but there's something wrong with the way it's written. What do you have to do to the bottom? Rationalize it. Beautiful, right? So what do you multiply by to make this become rational? Square root of 2. So then I would get 7 square root of 2. What's square root of 2 times square root of 2? 2. So 2 times 6? 12. So that would be tangent. And then, of course, you do the other one just by flipping those around. Yes? Is that cool? So once you get the first 3, the other 3 are just flip, flip, flip. Rationalize where you need to. Okay. So at the most fundamental level, all these trig functions are easy. If I have a right triangle, I can just figure out whatever side I'm missing and then just make all the ratios. That's all they really are. The little bit of calculation you got to do is rationalizing if it needs to be done, right? Otherwise, you're just setting up the ratios. Beautiful. Yes?
Can you multiply by 6 right 2 over 6 right 2 instead of like this radical 2?
You could, but then you'd have to reduce. Because now you're giving the top and the bottom a factor of 6. That would cancel. Right? So the 6 isn't the problem. The rad 2 is the problem. So I just focus on what the problem is. Yeah. Okay. All right.
How would you do the cotangent?
Oh, okay. All right. So let's see. So I could, if I was crazy, I could flip this and have to rationalize again. Or that is what tangent is. I just changed it around, right? I just made it look different. So it's cotangent. Isn't it just flip this? Yeah. So cosecant, secant, and cotangent are just flips of the original 3, right? But I'm not going to flip. I'm going to flip what it started off as, because then the radical's on top. I can leave it alone then. That's awesome. Okay, maybe. Okay. So that's all trig functions are. Is ratios of sides of right triangles. Okay, I like it. Now, real quick. It's not the best one to do this on, but oh well. Can somebody? All right, I'm gonna erase this for a second. Help me out. If I blew that triangle up, if I doubled the size of the triangle, can somebody tell me what the side lengths would be now? Well, how long would this be? 22. This one. 14. This. 12 rad 2. Is everybody with me? What would this angle be? Does this angle change? Nope. I just sort of extended the sides. So I really just extended the sides out, right? So the angle is still the same. So what would sine A be? 14 over 22, which reduces to same freaking thing, right? Same thing. What that means is that the sine of an angle equals a number, period. It just always equals the same number, because no matter how big or small my triangle is, they'll always reduce to be the same thing. So we did, let me remind you something we did a little while ago. We took I'm going to try to, we already did this, but I kind of truncated this. We started with an equilateral triangle. X, X, X. We cut it in half, right? So what were all these were 60 degrees. So we cut it in half here. You guys remember doing this? So then I have, if I just redraw this piece, I have this right triangle here. How long is this side here? X over 2. This is still 60. How big is this angle here? 30. And this is X. This is H. Can you figure out what that height is? Remember, we did this before. Wouldn't that just be Pythagorean theorem? Kind of gross, because there's not many numbers, right? But isn't it just x squared equals h squared plus x over 2 squared, right? We did this. I don't know if you guys remember. Let me keep going. So therefore, h squared equals x squared minus this. Everybody with me on that? What's x over 2 squared? It would be x over 4, x squared over 4, sorry. What's a full x squared minus a fourth of an x squared? A whole thing minus a quarter. 3/4 of it, right? So then what's h? You're going to take a square root, yeah. What are you doing up there? No, I don't want to do that. Well, all right, you're just gonna, hey, I'll pretend like I did something. So I would take a square root. Is everybody with me? I'll just take a square root, right? So I get, so let me put this up here. So I get, right now I got h squared equals 3/4 x squared. So if I take a square root, square root of 4 is 2, square root of x squared is x. I pick the positive one because it's a length. So this is square root of 3 over 2 x. So, what is the sine of 60 degrees? Right, 3 over 2x over, right, is this side divided by hypotenuse. And of course, what cancels? The x's. So the sine of 60 is just equal to the square root of 3 over 2. That's what it always is. Because if I make the triangle bigger or smaller, it's going to reduce to be rad 3 over 2. You like it? What about cosine of 60? It's going to be what side to what side? Cosine is the x side. So it'll be x over 2 over hypotenuse, x. So the x's cancel, I get 1/2. So cosine of 60 degrees is 1/2. That's what it always is. I like it. Maybe. And then, of course, tangent. I could do this very quickly. I pointed this out before. I can just do it straight. But just to kind of show you guys, tangent is equal to sine divided by cosine. Which is nice because I know what both of these are. This is rad 3 over 2 divided by 1/2. See how the 2's cancel? The over 2's cancel? So you just get rad 3. Interesting. We did something similar with, let's see if I can make this sort of to scale. That's a little better, okay. We did something similar to 45, 45. We did this before. These have to be the same length. So therefore, the hypotenuse would be h squared equals x squared plus x squared. H squared equals 2x squared. Is everybody cool with that? If these are both 45, their mouths open the same amount. This must be the same as this. So I'm going to call them both x because I don't know what either one is, but I know they're the same. And then I can figure out what that hypotenuse is. So then what's the sine of 45 degrees? It'll be this side divided by the hypotenuse, right? So it'll be x over rad 2x. So it'll be 1 over rad 2, and if I rationalize that, I get rad 2 over 2. What's special about the cosine of 45 degrees? It's going to be the same thing, because these are both the same length, right? So it kind of makes sense, at 45 degrees, the x piece and the y piece are the same length. So I'm going to get the same thing eventually. And what's tangent? 45 degrees. X over x, which is 1. So anywhere in the whole universe, if I see tangent of 45 degrees, I can replace that with 1. That's what it is. Okay, maybe. So let me do this. Let me finally do something. Maybe some of you guys have been sort of like, when are we going to do this? Oh yeah, I was supposed to do that. I'm sorry. We'll do that in a minute. It's kind of leading up to this anyway. So here's that unit circle, meaning the radius is 1. Okay, so let me do a little something. So if I draw in here 30 degrees. All right, so this whole thing, so let me put a 1 here. There we go. So this, the radius is 1, right? Okay. This is the x side, and this is the y side. So what do we know for about 30 degrees? Well, one thing we know is what's the sine of 30 degrees. So we sort of did that earlier. Oh, let me see. I should start with the 60 because we just did the 60. Yeah, let me start with the 60. Draw. There we go. Just talking about the 60. We did the 60 just now. So this will be the x piece of this. This is the y piece of this. Okay. And real quick, this is kind of nice that this happened. Do you see how when I move up, when I go to 30 degrees, this is x, this is y. When I move up to 60, did x get bigger or smaller? Yeah, it was here at 30, now it's here at 60, right? Of course it got smaller. As I turn this around, my x piece is going to keep getting smaller and smaller. Did my y piece get bigger or smaller? Got bigger. Of course it gets bigger. As I rotate it, it's going to have a bigger y piece, right? Okay, I like it. So at this one, what's cosine of 60 degrees? We just did it a minute ago. Say again. 1/2, I love it. And what's sine of 60 degrees? Rad 3 over 2. So what that means is, okay, what that means is, and again, this is 1, right? So that means that this piece here, so cosine of 60 degrees is x over 1. Cosine of 60 is 1/2, so x is 1/2. So this much is 1/2. So the x is shrunk to be 1/2. And the y, in much the same way, sine of 60 is the y piece over that hypotenuse, right? Well, we know sine of 60 is 1/2. I'm sorry, cosine of 60 is rad 3 over 2. So this much is rad 3 over 2. Okay, all right. Yes?
Does it matter which side of the angle is on the triangle to find out what's like cosine and like sine?
The angle has to be in the base. Do you see how there's an angle up here?
Yeah.
Right? There's an angle right here, correct?
Yeah.
Can anyone tell me what that angle right there is? Say again? 30, right? Because that's 90 here. That's 60. It's 150 so far. So that must be 30. Right? So in order to talk about sine, cosine, tangent, all that stuff, the angle has to be in the base. It has to be here. Okay, I like it, I like it. So in the unit circle, as I rotate, I'm creating these differently shaped right triangles. As I rotate further, the x piece gets smaller and the y piece gets bigger, right? Which trig function goes with the y side? Sine. So as I increase this, sine is going to grow bigger and bigger and bigger and bigger. Cosine likes x. So as I increase this, cosine is going to get smaller and smaller and smaller because the x side gets smaller, smaller, smaller. Does that make sense so far? Any sense? This is why cosine likes y, cosine likes x is better than SOHCAHTOA. It will take you further than SOHCAHTOA will. You can still use SOHCAHTOA. still fine. It's just not where you want to stop. Okay. Something else I want to point out. Can anyone tell me, looking at that blue triangle, since it's easier to see, can anyone tell me what x squared plus y squared is? Look at that blue triangle. In fact, for each triangle, this is true, but it's just easier to see the blue triangle. What's x squared plus y squared? 1. And isn't x the cosine piece? Now be careful, x doesn't equal cosine. It's because the hypotenuse is 1. Cosine is x divided by this, but that's divided by 1. So this is the cosine piece. What am I calling it? It's just, well, let's just say theta. Y is the sine piece. So we've got our first little identity. Sine squared plus cosine squared equals 1. And instead of writing parentheses with the 2 out front, we just put the square right there. That's just a choice in notation. We decided to not keep having to put parentheses forever. We just put the square right there. So that means the same thing as this. So sine squared plus cosine squared is always 1. Okay, let me show it to you a different way. Real quick. All right, so if I give you a triangle, let's see, what's cosine theta? X over h. That's the definition of cosine, right? There's nothing to do there. It's just the definition. What's sine theta? Y over h. So help me out. What's sine squared theta plus cosine squared theta? Sine theta is y over h. That's y over h squared plus cosine theta is x over h. Stay with me. Is that cool so far? So I just figured out what that is, and then I just wanted to know what that equals, right? Sine squared plus cosine squared. Isn't this y squared plus x squared over h squared? Is that cool? They both are over h squared, so I can put them together. What is x squared plus y squared? H squared. So sine squared plus cosine squared is always 1. If the angle's the same, right? So if I said, what's sine squared 30 degrees plus cosine squared 30 degrees, you don't have any work to do. It's 1. That is an identity. It's a known fact. Why does it make sense? Because sine is the y side of a triangle with hypotenuse 1. Cosine is the x side. So of course x squared plus y squared equals 1. We know that. Okay. So there's 2 different ways to see that this is true. All right. Okay. So let's see. Let's try this. Let me take this away. It's a bit messy. So let me try this. Here we go. So this is radius 1, right? So that's 1. That's 1. That's negative 1. That's negative 1. Radius is positive 1, but if I put it at the center of the origin, it's got to go up and over 1. Right? So it goes back 1 and it goes down 1. Okay. So if I am at 0 degrees, right? I can't make a triangle. To make a triangle, I have to move it up a little bit. Then I can make a triangle, correct? But you can tell me right here, what is the x piece? How long is x? 1. The whole thing is x, correct? Which trig function likes x? Which trig function goes like x? Cosine. Cosine is happy at 0 degrees because it's all x. Cosine likes x. So cosine of 0 degrees is 1. So cosine starts big and then it gets smaller. We saw that earlier. As I rotate, doesn't my x piece get smaller and smaller and smaller? Okay, stay with me now. Okay. What's sine of 0? Well, sine likes what side? Y. So if I have this, is there any y piece to it? No. Cool. So then what's sine? If sine likes y and there is no y piece, what's sine of 0? 0. There's no y piece. How long is the y piece? 0 shift. Okay. I'm going to get this all out there, and then I want to show you a really cool pattern to help you remember. You're going to memorize, you just are, you're going to memorize these values. You must know these values. If I rotate to 30 degrees, do I have a y piece now? Yes. And in the x piece, what's happened to it? It got smaller. So cosine of 30 degrees, it's gotten a little bit smaller. It was 1, now it's a little bit smaller. It's going to be rad 3 over 2. Sine of 30 degrees was 0, now it got a little bit bigger. So it's going to be 1/2. Okay. In fact, let me say this real quick. I should have said this earlier. That's all right. Sorry. Just hold that for a second. I really want this, on one level, I want this to make all the sense of the world. Sine was 0 here. If I go to 30 degrees, sine grew a little bit. Yes? Because now there's a y side. It's not very big yet. It's just 1/2. Cosine, the x piece, shrunk a little bit. So it went down to square root of 3 over 2. Now, real quick. One little thing on the side here I want to show you. We haven't really talked about 30 degrees directly yet, but I want you to realize something. We did this one earlier. This was x over 2. This was x, and this was 3 over 2x. And there's, what's this angle here? 30. Sine of 60 was rad 3 over 2x divided by x, right? Bam, so that's why it's rad 3 over 2. Right? Because sine is the y side as long as the angle's in the base. What if I ask you what the cosine of 30 degrees is? Is it in the base? Do you see how 60 is in the base but 30 isn't, right? So if you just do this, right? If you just rotate your head, what's the x piece? This guy, right? So cosine of 30 degrees is equal to rad 3 over 2x over x. Bam, rad 3 over 2. So this is really interesting. It should make sense. Because a 30, 60, 90 triangle, if I rotate it, all the sides are the same length. So the sine of 60 is the same thing as the cosine of 30. And if you look in the picture, if I just sort of fast forward to 60 degrees. Right, so here's 60. Do you see how this triangle is the same as that triangle, just rotated? Right? So it kind of makes sense that in this case, that now I'm way at 60. What's gotten way bigger? This y side has gotten way bigger, right? So which trig function has gotten bigger? Sine. So sine is going to be rad 3 over 2 now. Cosine, look how tiny cosine's piece is. Look at that little dude. Sorry, the cosine didn't mean to make fun of you. He's a little tiny dude, right? So that's going to be 1/2. So I really want you to notice something. Cosine starts big, shrinks, and then at 90 degrees, is there any x piece? At 90, it's all y, correct? So what's the cosine? If cosine likes x, and I'm here where there is no x, what's cosine at 90 degrees? 0. There's no x piece. So of course cosine is 0, because cosine tells me how long the x piece is. What's sine of 90 going to be? 1, because it's all y. How long is the y piece? Freaking 1. It's all y. This is another reason why the biggest output for both is 1. That's the biggest they could be. Okay, maybe. So I left one angle out. I have one more color, so that's good. 45 degrees. This is where they both agree. It should make sense. If I get to 45 degrees, they're equal. It's right in the middle. So this is where cosine, oh, poor little red dude, cosine of 45 and sine of 45, they are both rad 2 over 2. Okay, so these are the things you have to memorize. You have to memorize that cosine of 60 is 1/2 and all and so forth, everything else, right? Sine of 45 is rad 2 over 2. How do I memorize these things? The closer I am to the x-axis, the bigger cosine is. The further I am away, the smaller cosine gets. The closer I am to the x-axis, the smaller sine gets. And the further away I am from the x-axis, the closer to the y-axis, the bigger the sine gets, right? So I can't do that shit for you. Okay. So I want to point out something really crazy. In fact, all right. There's a lot going on up here, I know. Can somebody tell me, what's the square root of 0 divided by 2? This is going to seem like it's totally out of nowhere. Just go with me, go with me. What's the square root of 0 divided by 2? 0, correct? Okay. What's the square root of 1 divided by 2? 1/2. What's the square root of 2 divided by 2? What's the square root of 2 divided by 2? What's the square root of 3 divided by 2? What's the square root of 3 divided by 2? What's the square root of 4 divided by 2? Yeah, square root of 4 is 2, divided by 2 is 1. All right, what does that have to do with anything, Jeff? I don't know. Oh yeah, I remember. It's kind of cool. It's kind of crazy. Let's just look at sine for a second. Right, let's just look at sine. I'm just going to focus on the first quadrant here. So at 0, it's 0, which is square root of 0 over 2. At 30, and just to remind you guys, what is 30 degrees in radians? So right now I'm just talking about degrees, just because we're used to degrees. I want us to get used to sine and cosine, but let me just remind you, or you remind me, how many radians is 30 degrees? Pi over 6, because 180 divided by 6 is 30. That's also known as pi over 6. So what is the sine of 30? Square root of 1 over 2. What's the sine of 45? Square root of 2 over 2. What's the sine of 60? Square root of 3 over 2. What's the sine of 90? Square root of 4 over 2. That's almost too nice to believe, right? Square root of 1 over 2 is 1/2. Square root of 2 over 2 is square root of 2 over 2. Square root of 4 over 2 is 1. I'm hoping that helps you memorize what sine does. Okay, maybe. No? You guys don't like that at all? So again, we proved each piece of this. Now I'm just trying to show you sort of an overall pattern to make it easier to memorize. Right? Okay. And what does cosine do? Cosine does the exact opposite. It starts at 1, and then as I move, it decreases through the same way. Maybe. And again, please let this be nice. Why does sine grow? Because as I rotate, the y side gets bigger. So of course sine is going to grow, because sine is a measure of how big the y side is. Let me ask you a question real quick. If I give you this triangle here, let's say this is 5, and this is, it doesn't matter, Jeff. 3, 4, 5, sure. And I give you this triangle here. This is 12, 5, 13. Can somebody tell me which one's bigger, sine A or cosine, or I'm sorry, sine A versus sine B? Can you do it without calculating what they are? Which one's bigger? This one, because that's way longer than that, right? So again, it's not drawn to scale, but still. So this y piece is so much bigger relative to the x piece than, and this is smaller than the x piece. Maybe. So again, sine is related to how big the y side is. When it's tiny, sine's going to be small. When it's really large, sine's going to be big. Okay, I like it, maybe. Okay. So let's talk about, there's a whole range of things we haven't talked about yet. We've only talked about the first quadrant. Okay, so let me look at the second quadrant. Let me draw it by itself, because this is a little bit insane. I might be able to do it. Let's see. It's a little insane. So let's talk about 150 degrees. Now, with my crappy drawing skills, this doesn't look apparent. But aren't these green triangles the same size? Because how big is this angle right there? 30. So aren't they the same triangle, right? Okay, so let's talk about sine. What would the sine of 150 degrees be? Say again? Yeah, it's okay. It's the same as the sine of 30. These triangles are the same, do you guys agree? Because they both have the same angle in the base, 30 degrees, right? I don't know if you guys remember what I called this. This is a certain kind of angle. I almost gave it away. Do you guys remember what I called this angle? It's related to the x-axis. It is the reference angle. Yeah, so that's a reference angle. Heretofore known as the RA. If I know the reference angle and I have memorized all the values in the first quadrant, I know the angle I'm given, even if I'm outside in a different quadrant. So what's the sine of 150? It's going to be the same thing as the sine of 30, because that's the reference angle. Also, is y positive or negative here? Is y positive or negative in this quadrant? Positive, correct? Okay, so sine of 150 is the same thing as sine of 30, which is 1/2. Cool. What's different with cosine of 150? What's true over here? What's x, positive or negative? Positive. What about here? Oh shit! Cosine likes x, correct? So cosine of 150 is going to be related to cosine of 30. It's the same triangle, but it's just going to be the negative of what it was here. So it's going to be negative, right, 3 over 2, because it's in a quadrant where the x piece is negative. Rad 3. Okay. So like, for example, in this quadrant, what's true about sine and cosine? What signs, S-I-G-N, will they be? Positive or negative in this quadrant? They're both going to be negative, because x is negative and y is negative, correct? They're going to have the same numbers. Please realize that that kicks so much ass. They're going to have the exact same numbers. They're just going to be the negative of what they would have been. So, for example, if I give you, let's do, what do you got, Jeff? I don't know, dude. 225 degrees. What is the reference angle? How much, what's this? What's this? 180. How much past 180 do we go to get to 225? 45 degrees past, right? So that's what this must be. I really want them. If I go 225 degrees, I went 180 plus 45. So the reference angle is 45 degrees. So, what's sine of 45 degrees? So what's sine of 225 degrees? Negative sine of 45, so it'll be negative rad 2 over 2. So when you go to memorize trig values, you just have to memorize this stuff in the first quadrant, Because it's going to have all the same values. Because they're all the same rectangles. I'm rectangles. That's also good. They're all the same triangles. So at 45 degrees, I should have done this in red, but too bad. I get the exact same triangle here that I got here. They're the same triangle. So of course they have the same side lengths. So of course the trig functions are going to have the same value. It's just that it's in a quadrant where y is negative and x is negative, right? Maybe. Okay. So let's try to do a problem directly related to what we just did. So if I ask you, what is the cosine of 330 degrees? Can you take a minute, draw this and try to indicate where that is? Don't say it. Don't say it out loud. Trying to figure it. Don't say it. Trying to figure out which quadrant it's in, and then what the reference angle is. Don't say it. Just to help you out a little bit. Is that a full rotation? Don't say anything, but can't you see how close that is to a full rotation? Do you see how that's exactly related to the reference angle? Okay. So if you draw this, which quadrant are we in? Fourth quadrant, down here. Because they've almost made it a full rotation. How shy am I of a full rotation? That's right. So that's the reference angle. So remind me, what's the cosine of 30 degrees? Here's what I think when I see that, especially if you're brand new to this. I really don't have them memorized. I just remember, I know the values, rad 3 over 2, rad 2 over 2, 1/2. I know those. And I go, okay, cosine likes x. 30 is really close to the x-axis. It must be the bigger one. Therefore, it is rad 3 over 2. It was cosine 60. Oh, shit. That's really close to y. Cosine doesn't like it there. It's the smaller one, 1/2. Bam. Right? So to be really honest, I never memorized cosine of 30 is rad 3 over 2. I just do that real quick. Right? So that's rad 3 over 2. So what is cosine of 330? What's x here? Is it positive or negative? Positive. So this is going to equal cosine of 30, which is rad 3 over 2. And again, I really want you, here's 30 degrees, right? Here's 30 degrees. Aren't these the same triangles? This one and this one. They're the same triangles. So they have the same lengths of sides, so of course they have the same cosine. Why is it positive? Because it's in a quadrant where x is positive. So real quick. Cosine, sine, right? In the first quadrant, they're both negative or positive? Positive. In the second quadrant, which one's negative? Why? Because cosine likes x, x is negative, but sine is still positive, because y is still positive. Third quadrant, they're both negative. Good, because they're both x and y are both negative. Fourth quadrant, x is positive, y is negative. Okay, right? You guys start to get a feel for this? So you only have to memorize the first quadrant, and then you just got to remember, all right, am I in a quadrant where the y is negative? Okay, if I am, then sine is negative, right? Maybe? Okay, so I think I'm finally to a place where I can talk about your question. Okay. We already did a problem like this, but I just want to remind you. Because all of this is nice and great, but on one level you're all like, okay, we're just playing with numbers. You got triangles. Good job, math people. You got playing with numbers again. You just keep it to yourself. But I can now do a problem like this. Could very easily show up in real life. Where's that check? question's gonna say, find all the unknown side lengths, right? That's what the question's gonna say. What the shit? Can I do Pythagorean theorem? Why not? Got too many things that I don't know, right? That kind of was like, yeah, that pretty much sums up my life, Jeff. Too many things I don't know. So what the shit? What am I supposed to do? So this is the only side I know. What trig functions involve this side? Sine. Okay, so let's try this. Sine of 60 is what? 6 over c, correct? Can't you solve that for c? Because what is the sine of 60 degrees? Oh shit. Rad 3 over 2. So let me give you a cool little trick to solve these things. Can't I just flip both sides? Do you see that? What's wrong with this is the c's on the bottom. I'm trying to solve for c. So let me just flip both sides. How do I solve for c? Yeah, so multiply by 6, right? So you get c equals 12 over rad 3, right? And of course, what's wrong with that? One little thing's wrong with it. It's the right answer. It's just, you got to do what to it? Rationalize. So you have 12 rad 3 over 3, which is 4 rad 3. So before, we had to know two sides to figure out the last side. Now, I just have to know a side and an angle. And then I can do everything. Now, how can I get side A? Two different ways. Yeah, I can just do the Pythagorean theorem now, right? Because I got two sides. Or, what trig function relates these two? Tangent. I could do tangent of 60 equals 6 over A, right? But what would I do instead? What would I rather do? I'd rather do just Pythagorean theorem, correct? Because now I have two sides. I might as well do Pythagorean theorem. So that's the immediate thing trig. And the example I did last time was we have some tree. I don't know how tall it is, but I can walk out and see how far this is. And then I can use trig to actually figure out how tall the tree is without having to climb the tree, right? So trig immediately helps us with surveying and just stuff like that. It helps us with astronomy too. My God. Figuring out how far apart two stars are and how far away they are. We use trigonometry there. It's crazy. Okay. All right. that's okay. It's not as far as I wanted to get, but that should help you with that problem though, right? Okay. I think that's plenty. We're basically at time. So tomorrow I'll have the quizzes graded. We'll keep on going. Hopefully I'll give you guys the updated homework sheet, but I did tell you, when's the next test? Do you guys remember? November 2nd. Yes. We'll see if it stays there. I might move it back one more day. We'll see. Okay, so I'll give you an updated homework sheet tomorrow.